So let's start the talk. That's on hierarchical Bayes models for inverse problems. So you have seen what is the inverse problem, what is the forward problem. I'll be more with the inverse problem here. And this is a serious collaboration with Yalchin FNDF, who is an applied mathematician, Bangti Jin, who is now in UCL, another applied mathematician, and the student Karen. The statistics part has been done mainly for my postdoc, Nilabji Guha, who is now in UMass. So by serious collaboration, I mean it's not only data generation and analysis. Some of the parts still I'm learning, especially when I'm doing all this multi-scale stuff and things like that I'm learning from Yalchin. How to do finite elements, how to get into multi-scale finite elements and stuff like that. And you need it. To solve this kind of problem, you need statisticians and mathematicians together. So let's see why we need this method. So we all talk about data science and stuff like that. So we have massive data, structured, unstructured data. So we know that there are highly heterogeneous data, we have hierarchical models, we know how to get them in, stuff like that. We are using statistics, we are using machine learning, predictive sciences, whatever you say, all these things are going on. Sometimes they're very good when what kind of problem you're solving. Are you solving marketing kind of problem? Good. Social networks, good. But when you come to more scientific problem, there is a scientific model. And if you try to blindly use this kind of very flexible database method, you may miss that. So there's an integration it's needed, and that's a talk about. So statistics provides you a coherent way of looking at the data, but in many application areas, there are enormous amount of information. They're coming from physics, chemistry, you have seen in previous talks, especially Professor Odin's talk, how science can come through partial differential equations. So you have to work together. And my definition of data science is this. I know everybody, data science, everybody is doing data science these days, and they have their own definition. My definition of data science is when data comes with science. Because there are two philosophical people. One, like moralist, told, all models are wrong, but some of them are useful. I know another class of people in physics who believes all data are wrong, but sometimes they're useful. So, and this is the integration of this kind of philosophies where these two people come together and they're trying to do something, okay? And that's we are trying to do this combination of data-driven method with physics models or PDE-based models. Computer experiments, already you have seen these things that these days labs are very expensive. And most of the times when you're not getting labs, you're going for simulations. This is a very good example when President Obama came up with this material genome project, telling you want to find out a new materials. It's very expensive, very time consuming to do the experiments. Can you do some kind of modeling? So where you don't have data, so the philosophy is where you have data, use it. Where you don't have data, simulate, use models, mathematical models, and integrate them, okay? So that's the simulation. So experiments expensive, you have mathematical or physical models, and you can simulate from there. And you can get these predictions. And you have that we call algorithm or code. So we'll see how statistics and these codes can come together. And but they need some input parameters. All these codes and stuff, they need some input parameters. You are using Darcy's law, you need permeability. You are using heat equations, you need some boundary conditions. And those things, if you try to think that you know, sometimes you can do wrong predictions. So inverse problems will tell you how to estimate those parameters with uncertainty. So by mathematical model, what I mean is, these are physical experiments, it's a set of equations. These are big partial differential equations. And what we heard from previously, they're very expensive to solve. Some of the resolver-based equations, if you do in a very fine scale, it can take weeks or months to run them. So they're very expensive. So how to handle them in statistical way, we'll see that. In an inverse problem, when you use these mathematical models, you have some unknown parameters to run those PDEs. The whole problem, inverse problem is saying, and this solution of PD is a forward problem. What inverse problem is saying, if you have some data, that means output with noise, how we can use them to estimate these parameters. So that's a very big deal. So a lot of applications, petroleum engineering we do, some of the aerospace engineering, earth science, a lot. I didn't write down all of them. It will fill up the slide. We write it down in this way. We are using an additive equation where y the response, k is the problem, k is the forward problem, u is the unknown parameter, and plus some error. If you see anybody in statistics will say, we start our undergraduate statistics with this kind of equation. But they're very different than what we do in statistics. Usually these Ks are for us linear models, spline models, wavelet models, but here these Ks are like codes, they're like simulations. Okay, so that's a big difference, and they're very expensive. So the main deal is we want to estimate U. That's the unknown parameter, which are the inputs. Without U, we cannot run it. You have some data based on that. You want to estimate U's with some uncertainty there. So that's the picture. By forward problem, I mean you have an input parameter for U. You just chuck it in inside the PDs. You run it, you get a solution. That's your KU. That's your output. Inverse problem is saying, suppose you have some observation. Which is this output plus some noise? Noise could be Gaussian, noise could be something else. We'll see here. Can I invert the whole thing? Can I estimate U with uncertainty? So that's the inverse problem. That's what we are trying to solve here. Pretty simple. So the examples here will take us very toy examples. One will take porous media characterization. If you live in Texas, you are doing oil is the fuel of life there, so you have to work with oil. Reservoir simulations. So one of the examples we'll take where you have flow of water oil. You are using some Darcy's law kind of equations. The flow depends on the permeability, how permeable your reservoir is. That's the oil engineer tale. So when I go to the oil companies, the question is drill or not to drill. That's the question they ask. You can ask, you can give it the scientifically way, or you can toss a coin, or you can go to a prophet. Whatever you do, that's the answer they're looking for. And the drill or not to drill depends on the reservoir characteristics, how permeable they are, how many rocks are there and stuff like that. We'll see some examples on that. Another, we'll see heat distribution on the boundary of an object. So if you want to see the heats, suppose you have sensors, but you can have sensors in other parts, you want to predict what will happen in the boundary. One example sometimes we worked with here, I don't have the examples, that with UT Austin, re-entrance of spaceship. So you have all the sensors inside the spaceship. You try to predict what will be the temperature outside. But that was a very difficult problem. There are very high dimensional PDs. We'll have a very simple toy example on that. If you want to look at a book, that's one of the first books where we talked about large-scale inverse problems and UQ. Look at the editors. I learned a lot from this book. If you buy this book, I get 3 cents or less. And when I teach, I use Ralph's book. But this book has something which is mainly about large-scale inverse problems, very huge inverse problems. Different way, you have polynomial chaos way, you have spline functions way, and a lot of people who wrote in these books are sitting here. I can see their faces. All right, one example which I'll not talk much, but I'll give the reference. We work with the real data. You can ask, where is the real data? That was on real data. Center for Radiative Shock Hydrodynamics. It was in Michigan. Crash. Somebody, you can see some of my old buddies from the crash project sitting here. They work more seriously. We got some data here, which one from supernova explosion. This kind of explosion it happens very rarely, and it creates some shock waves. And it creates some very beautiful lights. So you can see that before this thing's explosion and after explosion, you can see this kind of light bands. Supernova creates radiative shock waves which passes through a region in which shock layers collapse in space. And actually, you can do it in lab. First time I learned that in Rochester, there's a lab which can do this kind of experiment to see their effect on materials. If you want to know more about it, we have some actual people who did these experiments are sitting here, somewhere here. We got some data. So what we want to see that, the effect of these things on materials. But the data is very, very expensive. So we have only a few data points. But we have a huge science. We have huge PDs. We have 2 papers, I'll give you these references, where we did emulators. We created basis function-based emulator, not Gaussian process. We did Bayesian polynomial chaos. It came out in Technometrics. There is another JASA paper, which is known as Beamer's paper, using polynomial things. So 2 emulators we created for this kind of thing. They work very well. They work very well in large-scale problems. Today I'm not speaking about it because I'm not talking about emulators. There are a lot of very big experts who are talking about it. We'll go using the direct things. So what we are going to talk today is, so Bayesian approaches to inverse problem, hierarchical Bayes model, and always you remember when you talk about Bayes, it's not Bayes' theorem. Bayes talk about structures. Always when you're a Bayesian means you can put structures at different stages. More structure you put, better things you get. Now if the assumption is wrong, you look at the sensitivity. But that's the way the whole Bayes thing goes on. Also, we'll do a separation of variable approaches. So in PDE literature, there is when you have a very big equation, you do separation of variables, some approximation, and you get some good things. Here also in statistical modeling, you do this kind of assumptions of separations of variables. Sometimes you can do good. All right, so inverse problem is like this, suppose. So suppose you have a Gaussian error. We'll go for some other errors later. So that's your likelihood problem. It's an ill-posed problem. Suppose you are looking at these outputs. They could be small, but actually the unknowns could be very different. That's an ill-posed problem. If you try to do least squares or maximum likelihood, you can get very bad answers. And you want to do some regularized estimation of this inverse problem. And in Bayes, regularizations and priors are very similar. Okay? All right, so what is a Bayesian solution? A lot of times my students ask me, why you are a Bayesian? I say, because it's simple. I cannot take very complicated thing. It's very coherent. Whatever you do, you have a prior, you put a likelihood, and at the end of the day, you find out posterior distribution. So you have a likelihood function of y data, what you're observing, condition on this unknown u. You have a prior distribution. You use your good old Bayes theorem to find out the posterior distribution of this unknown, product of likelihood and prior. Okay? So that's the Bayes theorem. And this is the Bayes solution of inverse problem. That is it. That's the solution. You solve it, you not only get an estimate, you get the whole uncertainty distribution. Buy 1, get 5 free. It comes with Bayes things. Uncertainty comes with Bayes things when you do these posterior things. So now the question is, why Bayes? Possibly all of you are already, I don't want to preach the preachers, but so you can get prior from the regularization, you can incorporate anything through the likelihood function, and you can put physical constraints, and you have a lot of computational-based approach. So what's the problem? Then you can ask me, the problem has been solved, so what else? The trouble here is it's not like usual Bayesian problem. Here, when you're writing this likelihood, this k is not a usual likelihood function. This is like a black box likelihood. This is a code. This is a simulator. You cannot evaluate it. You can run it. And I told you some of the reservoir simulation take months, weeks to run. So every likelihood evaluation you sit, suppose you are doing if you know about Metropolis Hastings algorithm, you just sit for a week and get some value and say reject or accept. That you cannot do here. So we need to run k to compute the likelihood function. So what we did before in a regression problem, a lot of us, we did this spline basis or anything else. We have a conjugate structure, we marginalize, we enjoy this computational simplicity. Here it's not possible. So what's the solution? There is a solution, MCMC-based solution. When you're doing Markov chain Monte Carlo, you have to be clever. You cannot go on doing rejection. So you can do ABC, approximate Bayes approximation things. You can do Hamiltonian Monte Carlo, where you use a lot of gradient-based methods. You can do multi-stage MCMC, we used a lot. But today I'm not talking about MCMCs. Possibly there are more experts who are going to talk about it. We'll talk about some other way how we can do it. We'll talk that you can reduce the dimension. You can use a variational-based method rather than exact MCMC-based methods. For these expensive simulators, sometimes they're very, very fast. And also sometimes we use these separable assumptions. You just take these as separable so that your likelihood function looks much better approximations. Prove some theorems that they will be close to the solution and then use them. So that way you can do much faster. And what is the third way? All of you have heard the last talk by Elaine. Use emulators. Just get rid of k, make a very good approximation using some kind of basis functions, Gaussian process, and use that for first solver. The first example I'll take is a linearized forward model. Very simple model with the heat equation. We'll see how to use that. Then we'll see how we can move for more nonlinear forward problem, which is much more complex. So let's start with this linearized case with very, very bad looking errors, because this is a boundary value problems. And whenever you get data in the boundary, the data doesn't look like Gaussian. They look very skewed and structured thing. So this is a problem. Very simple version of heat equation. There's no time effect, no source effect kind of thing. What it's telling you that if you have a rectangle like this, I have suppose some sensors here. I can observe here the temperature field. Can I predict the unknown temperature on some other surface? That's a basic problem. Now you can extend it in 3D, over time, over space shuttles, all those things you can do with more PD. But that's a very, very simple structure of the problem. You have a PD here over the temperature field. It's a very well-known heat equation problem. And you know that there are some boundary conditions. You are observing something on the boundary with possibly some flux estimates. So your likelihood function will depend on this kind of equations, okay, differential equations. So that's the basic problem. So to do that, what you get is how you write it down. Here I need actually Yalchun's help a lot. The applied maths, they use finite elements method. So I'm using a finite elements method here. I say, okay, this unknown temperature, I can span it with respect to some finite element basis function, say triangular functions. So that's what we used. So this is the function, you write it down, theta x. These wjx are basis functions, and uj's are the unknown coefficients. I want to estimate this u's. If I know the u's, I can exactly predict what are the temperature on this unknown surface. So that's the problem we are trying to solve. So when you have this finite elements expansion, you can write it down the data equation in terms of something called sensitivity matrix. And that's the calculation you need from these things. You can move towards this unknown surface. And you can write it down as a linear system. Y is equal to ku, where ku you know, you are the unknowns. So that becomes a linear inverse problem. The problem is ill-posed. It's not very good because it's a boundary problem. Many singular values of k's are close to 0. But you know some of the things. These u's are due to triangular basis function. These u's are the unknown temperature. You know that when they are adjacent points near to each other, usually they will be close. So the difference will be very small over the surface. So those are the structures you are trying to put here through this problem. So what happened here? When you have a boundary problem, when you have a data in the boundary, the observations are heavy-tailed or very skewed. Sometimes you have to truncate those things. So rather than Gaussian distribution, we plan to do skewed t distribution. Skewed t distribution means t distribution gives you flat tail. Skewness make it right or left skewed. So it is rather than Gaussian, like sigma square, you have two more parameters. One is degrees of freedom, which is controlling your tails, and there is a skewness parameter alpha. Alpha is negative, means you get left skewed distributions. Alpha is positive, means you get right skewed distribution. So you can put them here so you can cover outliers as well as you can cover any kind of skewed error distributions in this inverse problem setup. So you see it's a very general class where if you put alpha equal to 0, you go back to your good old Gaussian distribution. There is no skewness. But we are estimating it from these things. Also, if these degrees of freedoms are very large, you know t distribution go towards normal distribution. So Gaussian distribution or skewed Gaussian distribution is a specific case of it. It has a very complicated density function. If you write it down, it looks very ugly. It's not easy. It doesn't look like a Gaussian distribution. What you can do, the whole trick, again, if you, after lunch, if you don't want to look at the mathematical notation, you don't have to. But you have to know the trick. When you want to do this faster computation, MCMC or not, you need to write down some presentation. If you try to get this complicated distribution, it will take years to run. What you do, this complicated distribution has a scale mixture family. So you have a scale mixture of Gaussian presentation. You start with, this is a scale mixing. You start with a gamma mixing, you do some reparameterization, and you very nicely, you can write down the whole QT family as a scale mixture of normal distribution. What it gives you? When you do MCMC, if you want to do all conjugate distributions are known. So possibly you can avoid most of the parts, the metropolis hastings or anything like that. If you want to do variational Bayes, you can write it down as a separations things, very fast variational Bayes algorithm you can find out from there. So the trick is always when you have a very rough distribution, try to write down some kind of augmented distribution or mixture distributions so that you can handle them computationally much more easily. So that's about the error distribution. On the other hand, if you look at it, so that's my likelihood function if I use a skew t. But what is the prior on that? What I know about the system? I know there is a structure. I don't want to put a Gaussian prior here because I want to regularize. Also, I know that if you are close locationally, they will be small. The difference will be small. The people who are used to lasso kind of thing, they'll jump and say, oh, this is fused lasso. It's exactly you're putting a prior like this is same as doing a fused lasso. But we can do better things than that, fused lasso. So that will be your prior distribution where you are putting this kind of structure overuse. So how you do this lasso or fused lasso? You put an operator which takes the differences. You put 1 and -1 so that L times you get the difference of use. And then you write down a distribution like this. This is exactly Bayesian version of fused lasso. And it has a hierarchical structure. First part is a Gaussian distribution with a diagonal sigmas. And then you put an exponential prior conditional lambda. Also in Bayesian literature, they are very popular recently known as local global priors. So if you know as Paulson, Scott, and all this paper, they are doing these local global priors, where these local random effects are these Sj squares. These are shrinking you locally. They are taking some of the component towards 0, some of them are not. And global component is like a classical regularization parameter. And you can write them down exactly if you do these simulations, you get fused lasso with uncertainty. That's the hierarchical model for fused lasso. So you write down this PU given as the prior in this Gaussian. Then you write down the prior over this Sj squared given the global parameter as exponential distribution. And then you put a gamma mixing. Again, it's a scale mixture of normal. Knowing scale mixture of normal, now it's coming very close to these inverse problem solutions that the computational, the algorithms becomes fantastic, but you can capture very rich class of distributions. So you don't have to stop at fused lasso. You can do much better thing. So suppose different kind of prior you put for a size square, you get different distributions. So first, if you put exponential distribution, you get a double exponential family, the marginal distribution. That's Bayesian fused lasso. Rather than that, what we do, that's one of my very bad papers actually. We put a normal Jeffreys sparse prior. I tried to be a cheap Bayesian, so I say I don't know the hyperparameters, just use Jeffreys prior. I never thought that that's a improper prior and the posterior was improper. The mode was fine. Still I get the solution. But the uncertainty quantification was bad. So that's one of the papers very popular. Actually, Casella, he took this idea and he put a full Bayes things in the JASA paper. Then if you put an inverse gamma distribution, you get student prior. So any other distributions you are putting, you are getting different class of distribution. Recently, if you put a half Cosine distribution, you get horseshoe prior. Horseshoe priors are fantastic. These days we are working with horseshoe. Look at Carvalho's paper in Biometrica. So, but these all, if you look at horseshoe priors distribution, actually I should not say I was the original reviewer of that paper. The trouble of that distribution is it's very ugly looking. So that was one of the complaints. But you can write it down as a scale mixture of normal again. So computation you can always simulate from there with a very, very fast, efficient algorithms. So that's a nice thing about scale mixture. So you can find out your things. The nice thing about horseshoe is it shrinks very fast towards 0. Also, it is a heavy tail. So not a lot of distribution have that kind of properties. All right, so you write down your posterior distribution with your favorite prior, the kind of regularization you want to do. Now you have to do posterior sampling. So you can do MCMC based. Again, I'm saying it's a very complicated model. You have a skewed to distribution, you have a sparse prior, but if you give a scale mixture notations, at the end of the day, MCMC is comparably fast. But we also did variational based posterior approximation, which is very fast too, that we'll see. So what do you do in variational based? Variational based approximation is saying that if you have a posterior distribution, just approximate with something. So if that is your posterior distribution p theta given y, you get some approximation q theta, and then just get the KL distance between them. You can have your own metric. We do KL. You can do your own metric. These days people are using better metrics, and try to minimize it. And popular assumption is a mean field variational family, where you think that this posterior is separable. They're conditional and independent. You can multiply things. Is it a good approximation? Sometimes not. If it is not good, you may really underestimate the uncertainty. All right, so if you write it down and if you try to minimize it with respect to the variational based posterior approximation, you get a very nice expression. That is, each of these posterior marginals become exponential of expectation. Expectation minus I means take expectation over all other except the ith variable. And that comes to be very nice expression. This is very similar to Gibbs sampling. What we do in Gibbs sampling, we take all the complete conditional, but we simulate from here. In a variational based mean field, you just take expectation of that. Okay? So you get an expression of that. And most of the times in this kind of problem, this expectation comes out to be very explicit nature. You know this distribution. So the expectation is just changing the value of the parameters. Okay, so this is the example, one of the simulated example. This is the exact solution. So we are doing a boundary value problem. We are trying to predict some heat temperatures in one of these things. And we are simulating from here because it's the exact solution. I know the exact solution. And then I add some errors, some skewed errors and stuff like that. And then I try to do this analysis. So I took 80 observations, and there are 40 basis functions over the unknown things. So those are minor things. It works in, we tried with a lot of data sizes and a lot of dimensions problems, this kind of thing. Here I have the observations, and here I want to predict. I have sensors, heat sensors here I don't. Okay, so that's the problem I'm trying to solve. If you look at it, look this picture. The solid line is the exact solution. This is a variational based solution. But if you forget about skewness, I have a skewed error here. If you say, no, I want to fit Gaussian distribution as error, because that's common, people do it, you can miss the solution. This is the solution which is missing it here. Not only that, in the second picture, we did the exact one, MCMC and variational base. Actually, they're very close to each other. The solution comes out to be pretty good. So there's not much difference there in terms of solution. But look at the comparison in terms of time. For different sample sizes and different basis function I tried, this is in seconds. In variational base takes this kind of things in seconds. Whereas MCMC is almost 100 times longer. It takes much longer time, convergence issues and stuff like that. So this is a toy problem. Again, here both of them works, but I think in very large scale problems when you're trying to do in spaceship and stuff like that, variational base could be really useful. That can be done in real time. Actually, some of the solutions could be done. I'm not selling variational base, but that can be done. Now, now the problem is, most of the times we get nonlinear problems. This is a linear problem. It's fast. If you have a nonlinear problem, what you are going to do? Very hard to do variational base because there is no separability there. It is very difficult to approximate the posterior that way. People use first order Taylor expansion. Most of the times, it doesn't work in high dimensions. It's very hard. So one way is, again, we are Bayes. People who are following Bayes, they put additional structures. And that structures can help you to solve this forward problem. So again, you remember when you have a forward problem, one way is to do is going for emulator, find out a fast solver using emulators. Other way is do some approximation in this forward problem and try to solve it fast. That we are trying to do the second way. So porous media flow. I told you in Texas, you have to work with oil once to survive. So that's the thing. So we are looking at the flow equations, Darcy's law. So application is in oil production. So forward model is the models of flow of liquid. So mainly oil, so under the reservoir. An inverse problem, and it depends on the permeability of the field. So what they try to do from reservoir, they try to take the data, some data, and they try to estimate how the reservoir looks like, how permeable it is. If it is highly permeable, you can really capture a lot of oil. If it is very rocky, it's very hard to do, very expensive. So question is drill or not to drill. It depends on the structure of the reservoir, how it looks like. So permeability field. Now the difference is permeability is a spatial parameter. This is not 1, 2, or 100 parameters. It's an infinite dimension. Any spatial field is infinite dimension. So you need to get the whole picture. If you put a constant permeability, a lot of people do that in their Darcy's law. You just put constant permeability. You can fail badly because subsurface is very bad, ugly looking. So what do you do? So fluid flow usually go for pressure difference. So what I learned from petroleum engineers that how you get oil. Very easy trick. Just force water. You push water, water put the pressure difference and push the oil out. Okay, and that's the way they drill the whole thing. Reservoir having high permeability is very easy. You can capture a lot of oil from there. But if it's rocky, possibly you're getting 10 to 15% oil you're capturing from there. All right, so that's the equation you're looking for. It's called single phase flow. Another very simple equation. There are a lot of more complicated equations there. This U is the, sometimes we call water cut data, sometimes we call pressure field. What is water cut data? When the fluid is coming out, you look what is the percentage of water. Here forcing water with time, they're all oil first. Then what happens, it's becoming more and more water. At the end, you know there is no more oil because only water is coming out. So fraction of water is called water cut. So what you do, you're observing, and this kappa is the permeability, or K is the permeability field. So it's at different values in different location, and it has some parameters. We are thinking it's like a spatial process. We have some data, output data, say fractional flow data with some error. We want to estimate kappa. So that's the problem. So that's the way it works. That's your permeability field. That's your input parameter. You give it, you run your Darcy's law or whatever you have, and this is the fractional flow you are getting, percentage of water. Sometimes you get some observation over the permeability, additional observation. You have seismic data and stuff like that, satellite data. From there you can have some observation, additional observation about the permeability also. So what you do, the first thing is it's a spatial field. So there is something called KLE expansion, coronal wave expansion, very standard. It's also separability. It tells I can separate the spatial location with respect to randomness. So these are the random parameters, these are the spatial locations. And I can write it down as infinite sum. Finite data, you cannot handle infinite sums. So at the end of the day, you have to truncate somewhere. Then you take a covariance structure. You can take a square exponential over smooth structures or something else. And then what you do, you want to estimate the theta so that you can get an estimate of the permeability field. Everything is fine if you do those things. What we found, we did a full base. I'll show you the reference. Still, we get a problem. Forward problem is very messy to solve. It's not easy to solve. Why it's not easy to solve? If you look at the forward solution, if you do separable, one-way separability, still it's a product of these permeability parameters and some location parameters. You have to solve it. It's very hard because the permeability itself has large number of parameters. These are coronal wave expansions coefficients. So they're inside the forward solver. So it's very hard. So what we thought that we use sometimes this emulator kind of thing. They work, but it's sometimes hard to get the spatial parameters. We did a second stage separability. We say this is a high dimensional function AI mu, which is a function of all these things. Can we write down again? They are separable. So I have the marginals as a product. And each of these components are Gaussian process themselves. This is almost like interpolation. Gaussian process is same as interpolation with randomness. So almost I'm interpolating. That times it reduces the dimension of the problem very much. It works very well. And you can prove somehow that if you have infinite number of this kind of thing, you can approximate anything within some neighborhood. Also, that's your hierarchical model. You're observing some water cut data. That's your forward solution, which is a function of permeability parameters. You have some error here. Now we can write down this U in this way. You're expanding it with separability. You use this separability approximation with individual Gaussian process for each of these components. And at the end of the day, you're writing down this permeability as KL expansion. You're truncating it. It's a truncated KL expansion. So due to the separability things, you can run both MCMC and both variational Bayes. Also, if you like to be real Bayes, you have to these days prove some consistency theory, and you can prove that it's consistent. If you do these Bayesian things, you have enough data. I'm never comfortable with these things, but you can prove it. If somebody, editor wants to have something in the journal, so prove it. Anyway, so let's look at the simulation now. So suppose I have 30 KL functions I'm taking, and I have 50 data points. We are trying to do the whole approximation. You look at, that's the true field we simulated from. That's the variational Bayes solution. And that's the MCMC based solution. Again, variational Bayes works pretty well to get the estimates of this field. Also, you can get some of this distribution. You start from prior distribution of theta. There are some Bayes learning is going on. That's the posterior distribution of these KLE parameters. All right, this is the convergence. But anyway, don't look at introduction. I'm not starting the talk again. What it's telling you, it's actually introduction things because I'm showing only you the toy examples. Actual petroleum problem is here. You have multi-source data. This data comes from the prior model is coming from seismic output. These are sound waves. You have some rock fluid physics. They are creating prior. You have some other additional data. You have a fast simulation. You are getting reservoir prediction. And you have to do data integration. Seriously, if you want to handle this problem, you have to get all these things, and still we can solve it. A lot of places we are stuck. That's why we make some assumptions, and we are trying to get out of it. All right? Second problem is I was talking about this Gaussian process. Believe me, this reservoir is so rocky, they are not Gaussian process. They are not stationary. They are not go near to the stationarity. It's very hard to get a covariance kernel which will approximate this non-stationarity. What we found that it's much easier to create a non-Gaussian field. They are like channels. So we can think it's not Gaussian, but it's like a piecewise Gaussian. So we have channels or tunnels kind of thing where these are separate Gaussian processes going on with different covariance structure. How do you know the boundaries? We can estimate the boundaries. So what we did is we used this piecewise linear function to get the boundaries. The location and the number of pieces are unknown. This is a reversible jump problem. But you can run through it, you can learn about the boundaries, and at the end of the day, you can get some nice estimate. Let's look at some of the pictures. The first one, there is only one channel. So that's the true channel going on. That's the initial. We started from here. This is a realization when you're doing this MCMC draw after convergence. You see, you're learning, you're starting from here, then it started, piecewise lines started jumping on, and you're trying to estimate the surface. Same thing when you have two channels. You can do the same thing. This is the starting value, initial value. You go on doing this reversible jump. You start learning about the whole thing. So some of the things in this way you can learn. The problem is, this is not a 2D problem. This is a much difficult problem. So we have some solutions, rough solutions. Suppose this is the pictures. This kind of picture is very difficult to get from piecewise linear. We use basis function like level sets. If you use level sets method, in some way you can capture, I forgot exactly how we did it, but it works very well. It can capture very complicated channel structures, and you can learn from the data about them. In higher dimension, level sets also works there in 3D, and it can capture this kind of channels. Now the conclusion is, what we couldn't do and what we should do. I didn't talk about anything about fast posterior approximation we talked about, but not about MCMC. ABC works very well. We worked some multi-stage preconditioned MCMC. The whole method was, when you are doing MCMC, you have a proposal distribution. Use some kind of multi-scale methods. Use a chord scale. If you go through chord scale, then use fine scale methods to run the actual forward model. Chord scale solutions are much faster. So use some kind of multi-scale methods to make your MCMC faster. There are Hamiltonian Monte Carlo which are using a lot of other information from these PDEs, and that can be used. Otherwise, use fast emulator. You don't know the solutions, try to approximate with Gaussian process. There's a fantastic talk by Elaine, who was talking about it. Or use some kind of basis functions. We did, I'll give you some references. Gaussian process never can capture this kind of non-stationary processes. What's my aim? The problem with Gaussian process is very rich. Any basis function methods, if you take infinite number of them, it will some way, limiting sense will go towards Gaussian process under some assumptions. But it's working on covariance function. Looking at modeling covariance function is very hard because it's positive definite kind of thing. But there is a reproducing kernel approaches where from covariance always you can go to mean. And if you go to the mean function using this reproducing kernel approach, then this mean function you can use basis functions and stuff. We have two papers, I'll show you these references. One is in JAZA, where we used Bayesian math. We used polynomial splines. And we showed that it can capture very, very non-stationary structures. You can find out corresponding covariance function in Gaussian process, but that's very hard to find. Second thing is the second paper we talked about polynomial chaos. So polynomial chaos was there. I learned about it. Then we put in a Bayesian, that's a paper in technometrics, where we showed that you can use polynomial chaos as a overspecified basis functions, and you can do Bayesian selection, sparsity there. And at the end of the day, that can come out to be a very nice emulator. So it's a statistical way to look at this whole thing. But what we are missing is integration of data with science. What I mean by that? That's true data science. When I go to these all companies talking about this thing, nowadays we have a lot of unconventional reservoirs. These are like shell reservoirs. People who put a lot of money, retirement money on oil companies, they know that these shell reservoirs and stuff can kill you. When it goes up, oil price goes down because they try to compete with it. Convention and unconvention always fight with each other. So these kind of things, shell reservoir has a lot of rocks. So these Darcy's law things don't work very well. These simulators don't work very well. You need a lot of local solutions. So what people do is they do decline curve analysis. We'll have a paper roll out on this kind of models. These are very much machine learning based method. This is like a survival model. How much oil you have. But at the end of the day, they use deep networks, this, that. That works there. The problem is when you try to use them for prediction in another reservoir, it doesn't work because there is no science. So problem is science and machine learning coming together. Sometimes you have to integrate, and we don't know how to integrate this PD with physics laws. How can you do? It's a very hard problem, actually. So that's one of the projects we are trying to solve, integration of machine learning methods with PD likelihoods. Very hard. Company, it will be much harder, in fact. All right, some of the references talking about our works. The first two came out in Journal of Computational Physics, where we did this variational Bayes with sparsity prior P's. Here some of the approximation, where you did this approximation of the forward models. This paper in Technometrics actually talk about full Bayes method. There are a lot of reversible jump. When you are doing Carnot wave expansion, the number of terms we kept unknown here, we did reversible jump things. It is a full Bayesian hierarchical model specification of this uncertainty inverse problem, but sometimes they're expensive. This Chakrabarty's paper, we have two papers, one is in JAZA, one is in Technometrics. These two papers talked about this radiative shock paper. They have the real data. Here we use a spline-based method, B-MARS method, which is very popular now. It's actually a linear system, so you can scale it up. This paper came out in JAZA. This is a recent Technometrics paper where in overspecified basis function we use this kind of orthogonal basis functions. And we showed that, in fact, they're faster than using spline-based, because the orthogonality property help you to get out of the things. What you can do in a Bayes way, it's overspecified, but you can put sparse priors to find out the proper number of basis functions, and they are also becoming. So these two are emulator papers, but they worked on basis function rather than Gaussian processor. Thank you. Thanks a lot for your indulgence.